So we had discussed if we have capacitor and inductor, the capacitor is charged, what's going to happen is the current's going to flow, the inductor is going to make it overshoot, it's going to reverse charge the capacitor. Now the capacitor is going to discharge the inductor, it's going to overshoot, and so you oscillate. And we'd said the frequency of oscillation is 1 over 2 pi square root LC. And so we derive, but the reality is it's a little bit more complicated than that. And that's because there's always going to be a little bit of resistance. So there will always be some resistance in a circuit. The wires have some resistance, and sometimes you actually put some circuit element in there. You put a resistor in there, you put some other circuit element you're trying to drive, and it's got resistance. And so now what happens is, as the current is flowing, you're dissipating power through the resistor. Otherwise, energy is just going back and forth between the two other elements. The capacitor and the inductor just share the energy without loss. So the energy in the capacitor is going to be Q squared over 2C. The energy in the inductor is going to be 1/2 L I squared. And so, but what's happening is the total energy in the circuit is going to be the energy in both of those. But that total energy is, as it flows, the rate of change of that energy is going to be I squared R, because the power dissipated in the resistor is I squared R. We really ought to put a minus sign in there to indicate we're dissipating. It's decreasing the energy in the circuit. So we would say that the rate of change of energy in the circuit is equal to minus I squared R. So that's the rate of change of the UB plus UC equals minus I squared R. So that's the rate of change of 1/2 Li squared plus Q squared over 2C, and that's equal to minus I squared R. So we do the derivative, and we have the Li di dt chain rule plus Q over C dq dt, okay, equals minus I squared R. Okay. And so we look at that and we say, well, okay, so dq dt is I. So we have Li di dt plus Q over Ci equals minus I squared R. So we can divide through by an I everywhere. So now we have L di dt plus Q over C equals minus IR. Okay. Well, let's move this over to the other side of the equation. So we have L di dt plus IR plus Q over C equals 0, di dt plus I R over L plus Q over LC equals 0. We know that I equals dq dt, so we have the second derivative of Q respect to time squared plus R over L times dq dt plus 1 over LC times Q equals 0. And so this is a differential equation that we want to solve. And, well, again, this is like the damped harmonic oscillator. And so you can look back at the damped harmonic oscillator as to how this equation was solved. What you get is that Q, which is the charge on a capacitor, is Q naught e to the minus r over 2lt times the cosine of omega t plus some kind of phase factor, where omega is now equal to omega naught squared minus r over 2l squared. Okay. And omega naught is the 1 over square root LC that it was before. And so this is the solution to that equation. Okay, what you notice is you get several regimes here. When r is very small, then not much happens in here. So if r is not very small, then what's going to happen is that omega is going to be very close to the omega naught. So if r is very small, then this is just going to be equal to omega naught. We have a sinusoidal or cosine type function, and then as time gets bigger and bigger and bigger, because r is small, it's not much of an effect, but as time gets very big, we have decay. And so what will happen is we call this underdamped. And so an underdamped situation, what happens is that you gradually get less and less. And so your circuit oscillates, but it gradually winds down. Now, on the other hand, if omega is, or rather, if r is very big, then what we discover is that the square root of omega naught squared minus r over 2l squared, this is your omega. If r is very big, then that becomes negative under the square root. Now we have an imaginary argument there. And so this becomes overdamped. So for an overdamped case, then what happens is Q over time, it just gradually kind of like drops down, asymptotically approaching zero. And so this would be a circuit in which you have a very big resistance in there, you charge it up, and it just very gradually drops down. But omega square root omega naught squared minus r over 2l squared, if r is just right, then what happens is, and by just right, that would mean that remember that omega naught squared is 1 over LC, and so that would mean r over 2l squared equals that, and so that would mean that omega is 0. So you could solve for what this would be. Okay, you could solve for r in this case, and so r would equal 4l over c squared. And so what would happen is 4l over c. 4l over c. In that case, if r is exactly equal to that, then we have what we call critical damped. Then the cosine term is a constant. And so now all that we have is, we have that Q equals Q naught e to the minus r over 2lt. And so what we have is exponential decay. And so this would be the case of a circuit that is perfectly matched, so that the circuit, when it's charged, it as quickly as possible drops back to zero, exponential decay. And so this would be your critical damp case. This would be if you don't want your circuit to oscillate, you don't want your circuit to have any transient behavior, you try to make it so that if something happens to it, it drops immediately or as quickly as possible back to its equilibrium state. So that is the case of critical damping. And so these are the examples here of damped RLC oscillations. Okay. As with The other sort of circuit, we made analogous, and just like LC circuit, made analogous observations to how that behaves in respect to harmonic oscillators. So this acts like a damped harmonic oscillator. We can also have a forced harmonic oscillator. So we can actually force oscillations in here. And so a forced oscillation would be an example of a driving factor, and then we have a resistor, we have an inductor, and we have a capacitor, and that's going to be a forced RLC oscillation. And so this is the essence of the AC circuit lab that we did in class before spring break. So, and this is what we'll be picking up with next topic.